Hello and welcome to today's video. In this video, we're going to talk about yet some other differentiation rules. Specifically, we're going to target composite functions and inverse functions now. So this is called derivatives of composite and inverse functions. Now let's go straight away to the first theorem. And that theorem is also referred to as the chain rule of differentiation. This is a theorem about composite functions. So we need two domains right now. We need two intervals, I, j, subsets of R. Let those be open intervals. Let x star be a point in I. That's the point we'll be interested in. And two functions. We start with g. That's going to be the inner function. So g will be a function that maps the interval I to another interval j. And f will then map the interval j to some set contained in R. So that those be functions such that what we want is g needs to be differentiable at the point x star. X star is in I, remember. And f, the function f, is differentiable as well. What we want to do later is we want to consider the function f of g of x. So f needs to be differentiable at g of x star. And we call that point y star. And what this theorem says is the composite function f after g is then also differentiable at the point x star. So then the composition or the chain of functions f after g. So it's a function from I to R because we first apply g. G is the inner function, and then we apply f to the result of that. So the function is defined on I. G maps that to j, and then f maps that to some set in R. So the point x star is here in I. That's mapped to y star, and then f maps that to f of g of x star, or f of y star. Okay, so this composition is differentiable at the point x star. And the derivative can be expressed in the following way. The derivative of f after g at the point x star is given by, what we do is we take the derivative of f at the point y star and multiply this by the derivative of g at the point x star. So this composition kind of translates into a multiplication when we do the differentiation. You could also say that is the derivative of f at g of x star. So you differentiate the outer function, and then you multiply the result by the derivative of the inner function g at the point x star. So this is the so-called chain rule of differentiation. And that, of course, is a very powerful rule because many functions are just compositions of simpler functions. So applying this chain rule, we can derive a lot of derivatives from a small set of building blocks. And we also have quite a few functions in our toolkit of building blocks. So that will enable us to differentiate almost every function that there is. The two exceptions up to this point are we have not discussed sine cosine, so the trigonometric functions, and we have not discussed the exponential functions. We make up for that in one of the upcoming videos. But before we do that, let's first talk about the second rule of differentiation that we want to discuss here, and that is a rule for the derivative of an inverse function. So that's the second theorem of this video here. That is about the derivative of the inverse. Of course, we again need a suitable setup. So let's again say we have two intervals, ij, both open intervals. And we have a bijective function between those two. So let f be a function with domain I and codomain j. And we want that to be bijective so that there is an inverse. And now the theorem says if f is differentiable at some point in x star, then we can have a look at the inverse of f and at the point that corresponds to x star, so f of x star. And the theorem gives us an information about the derivative of the inverse of f at this corresponding point. And what that precisely is, let's make that more precise. So if f is differentiable at x star in I, then the inverse function, that function is usually denoted as f to the power of minus 1. And please don't confuse that with 1 over f. That's usually a very different function, right? So f to the power of minus 1 is the inverse function to f. Now that is then differentiable at the point, let's call it y star, and that is f of x star. So the point that corresponds to x star through f. And we can even give the value of that derivative. So that value is f to the power of minus 1 prime at y star is given by 1 over f prime at x star. Or if you want to properly express that in terms of y star only, we'd have to say this is f prime at the point, and of course, if f of x star equals y star, then f to the minus 1 of y star equals x star. So this is f prime of f to the minus 1 of y star. Okay, so this is how you can compute the derivative of an inverse function if you have a function that has an inverse, so if the function is bijective. Now let's have a look at an example to see how we can apply that. And the function that we want to use here as an example is the nth root. So more precisely, for n in n, we consider a function f defined on the open interval from 0 to infinity, maps to the interval from 0 to infinity, and that's defined as f of x equals the nth root of x. Now, that is, of course, a bijective function, and the inverse is simply the nth power. So this function is bijective with f to the minus 1 of y is y to the power of n. So then if you apply f and then f minus 1, the result is again x, the value you started with. We already know about the derivative of that function here. We've discussed monomials already. So what we can conclude is f to the minus 1 prime of y, well, that is n times y to the power of n minus 1. And that means we can express the derivative of f itself through its inverse. So that is then the derivative of the inverse at the corresponding point y. And we know that derivative. We just have that up here. So that derivative is precisely n times y to the power of n minus 1. And now remember, y is f of x. So that's the nth root of x. So what we get here is 1 over n times the nth root of x to the power of n minus 1. And now let's try to simplify this a little. Now this is 1 over n, so we just take this factor here into a separate fraction times 1 to the power of x, and now we can express this as x to the n minus 1 and divide it by n. Remember, the nth root is the same as x to the power of 1 over n, so this is x to the power of n minus 1 over n. So now we have 1 over x to some power. Of course, that's the same thing as saying this is x to the negative power. So this is x to the power of minus n minus 1 over n. And we can split this expression here and say, well, this is the same thing as x to the power of 1 over n minus 1. What you can see here is, what that means is, if you have, remember, f of x equals nth root of x, which could also be written as x to the power of 1 over n. So what this means is the derivative of the function x to the power of 1 over n is 1 over n times x times 1 over n minus 1. So again, the rule we've seen working for monomials, take the power, write it in front of the x, and subtract 1 from the power, again works in this context as well. So you can even apply this to nth roots and it will work all the same. So this concludes our examples here. There's a lot more examples, specifically for the chain rule on the exercise sheet, so you'll have ample opportunity to practice that. And we'll go on with more details on differentiation. Specifically, we'll talk about the derivative of the exponential function and also the logarithm as its inverse in one of the upcoming videos. And I'll see you then, hopefully.